So I'll always be in omega fp, abstract probability measure. Okay, omega is some sample space surface, some sigma field. Let's call it sigma field. And p is the probability measure. Okay. Then, what would be the definition of a distribution function? So, distribution function is a map from R into 0 to 1, okay, such that if I want to compute the distribution, like the value of function, distribution function at x, what I need to do. So I need to compute the probability of a Borel set, and that Borel set would be minus infinity to x. Okay? Minus infinity to x. And such kind of a function, you call it a distribution function actually. Okay?
We represent f with sigma field, f for sigma field.
By the way, do you guys remember what's the meaning of the random variable actually? So we have defined it previously. So random variable is a measurable map, okay, on a probability space actually. Okay.
So f, we represent f for sigma field and also for distribution.
Oh, okay. Alright. So let's call it a calligraphic effect. It's fine. So it's any function from R which is defined in this manner.
Okay.
That okay. It's called distribution function actually. So we already know it meets with our intuition. We know lots of examples of it. Okay. What would be probability density function? Okay. So the probability density function. Okay, so I'm assuming that we all know what all these things mean intuitively, okay? That we have done course on probability, so we know what's a probability distribution and random variables and all these things actually. So I don't want to comment over things that, okay, what does a intuitively probability, this density function mean and so on and so forth, okay? So I'll just directly try to write it. Okay? So, any Borel measurable, so imagine I have a Borel measurable function f from R to 0 to plus infinity, such that its Lebesgue integral with respect to the Lebesgue measure, so it's like integral with respect to the Lebesgue measure over the whole omega is 1. Okay? So if a function is Borel measurable, okay, and its Lebesgue integral is 1, okay, the integral with respect to the Lebesgue measure is 1, then okay, is called the probability. Called the probability density function. Okay, it's called probability density function. Sorry. For the Borel set B. No. R on it. Yes, for whole R. Yes.
Omega is equal to R or what is
Omega would be R actually. defined abstractly and a few things for which omega I'm going to take.
PDF you have to define here, but restricted
Then it's a map from R to zero to infinity. So in other words, I'm taking a particular, okay, so for this I have what? I have R, B of R, okay, and you remember I gave you a question to solve in exam actually, on a probability measure. Okay? In a probability measure, Ex. Anyway, so if I have a Borel measurable map, okay, and for which such an integral is 1, you're going to call it a PDF. It's PDF of something. Okay? By the way, if this is the case, what would be the probability of a Borel set? I'm going to compute it.
From 0 to plus infinity. That is
0 to?
PDF values of 0 to 1 is the current.
Okay. You can call it, but 0 to 1 is a part here. So it's keeping it open that, okay, if I have any function,
Shouldn't be restricted.
definition is not restricting it. Okay. We can keep it 0 to 1 as well. Okay. But even if I write 0 to plus infinity, it's not mathematically wrong. It's fine. It's fine. So any such function, which is Borel measurable and has such property, you can call it that. So what will be the probability of a Borel set actually? So if you have, for example, such kind of a density function, then the probability of a Borel set would be the integral, okay, of f with respect to dm over the Borel set d actually. Okay? Is it making sense? And if f is, nice function and b is some, for example, like interval, so usually what we do, we define it for that what is the probability that, a random variable is between an interval a to b. And then we say that, okay, integrate it, a to b, okay, and then, but for example, if f is a nice function, okay, it has set of discontinuities, has set of measures 0, okay, and b is some interval, then you recover, what you have previously actually. This bit generalizes it actually. Okay. And obviously, I can also write my distribution function in the terms of this, and that would be, it's going to be, integral, the back integral of, what this f with respect to the measure m, but from minus infinity to x. Okay. Here's the definition. So we're going to say that the probability measure P, or the probability distribution P, okay, is continuous. We say that the probability measure P is continuous, or sometimes you use the word absolutely continuous, they all means. And if there exists, a probability density function such that you can, through which you can compute the probabilities. And this is an interesting and important point to make sense of it. let's think and ponder over this point. You have to keep one thing in head. So when you were, so previously when you were doing probability, so you have discrete random variable and continuous random variable. So we know that discrete random variable takes a bunch of values. For each value of omega, it has a value in R actually. And then what we do, that for example for discrete case, to each discrete value we assign some chance actually. Okay, we assign a number. And similarly, we do the same in the continuous case actually. Okay? So in both cases, in classical sense, we assume that there is a function actually which can model the probabilities of the random variable. That's what we assume. For example, when we did binomial distribution, for example, okay, then we know that the probability of x equal to k, I can write it in the terms of, okay, n choose k, and so it has a formula. So in other words, I can model, the binomial probabilities through a function. For example, Camel distribution, a function. Normal distribution, a function. So you have a function through which you compute the chances actually. Okay? Are you getting the point? While in measure theoretic sense, it's not necessary that you should always have a function actually corresponding who can give you the probabilities of the events actually. So if you have such kind of a function, so in other words, you have a probability measure distribution for which you have such a function, we're going to call it continuous actually, or absolutely continuous. But if we don't have such kind of a function, in other words, we can't model it through a function actually, which will not be the case. We will usually assume that, okay, we have some kind of a function to, compute the probabilities. Then we have to refer, then we have the only hope through which you have to compute the probability is this P actually, the definition of P. So you have to directly compute it from there, no other way. Are you getting the point? So this would work, this theory would work, okay, if F, so you have a partial PDF for what you call computing the probabilities. While the measure theory, okay, you have to keep in that while the measure theory is giving you, allowing you to compute the probabilities beyond PDF. It's not necessary that you should always have PDF to basically compute probabilities. But if you do have, you can compute it through the, the Lebesgue integrals. Lebesgue integrals. And if you have in a certain situation, a probability density function, you're going to call such a measure or such a distribution as continuous or absolutely continuous distribution.
What's the difference between probability density and probability measure?
There is a difference. There is a huge difference. So probability measure, okay, the probability measure, so it's like, okay, probability measure, it's not necessary that the probability measure should follow, or you can model it through a function actually. So when you say that you can model the measure or chances of happening things through a function, that's a very particular and specific thing actually. Okay, so it's like a very concrete thing. But it's not necessary that you always have a function through which you can compute the probabilities. I mean, if you don't have, the only way you have to basically compute the probabilities through the measure actually on which, through which everything is defined. So gradually this will clear up. So don't worry about it. Okay? So just pick the book and read it. So it was a comment that I want. So you see, what I want to do, I want to just make you realize that how the thing that you are doing now are different from the previous thing actually. Okay? Because previously we assumed that, obviously you need a PDF to compute probabilities. Obviously you need a PDF to compute the probabilities and CDF and all this actually. While what we are saying now that it's not necessary. It's not necessary that chances can be modeled through a particular function actually. maybe, there is no function which can model the chances actually.
The probability measure.
Then the probability measure is the only